So, let's finish up our discussion of general exponential and logarithmic functions. So, recall, we have defined the natural logarithmic function in terms of a definite integral, as follows. The natural exponential function is defined as being this guy's inverse. So, the natural exponential function is defined by way of this relation. So if y is equal to the natural log of x, then that means e to the power y is equal to x. Now, up until this point, I really want to point out that we have made no reference to exponents as they have traditionally been defined, right? Like, when do you first talk about exponents? Like third grade, fourth grade, maybe? You define them as being a notation for repeated multiplications. Not once has that definition ever been brought up in this discussion. Rather, we appear to have gone in a completely different direction, coming at it from the fundamental theorem of calculus. You know, we have defined this function ln basically just because we wanted an antiderivative for 1 over x, and then the inverse of this guy, as it happens, satisfied all of the same properties that we would expect an exponential function to satisfy. Therefore, we use exponential notation to describe it. But it has come from a completely different source, completely independent of the traditional definition of exponentiation. And I think that's fascinating. I think that's a really remarkable connection that is unexpected. In any case, part of what I want to explicate in this section is the actual connection between the natural exponential function, which, you know, comes from calculus, comes from this esoteric definition, and the traditional notion of exponentiation that you remember from elementary school, because the two are, of course, connected. If they weren't, then we wouldn't be calling these exponentials. And in so doing, we will also learn how to differentiate and do some basic anti-differentiation with more general logarithmic and exponential functions, namely ones where the base is not e. Right? Logarithms and exponentials where the base is not e. We want to know how to differentiate those dudes. Okay, so the derivative of natural log x is 1 over x. The derivative of e to the x is e to the x. Now, we want to connect general exponentials to natural exponentials. And this is actually pretty straightforward, how we can do this. So let a be any positive real number, and let x be any real number. This is true. A is equal to e to the power natural log a. Why is that the case? Well, because natural log and the exponential function are inverses of each other. So e and natural log cancel each other. So this is a perfectly valid expression. Consequently, if we have a generic exponential phrase like a to the power x, that is the same as e to the log a to the x, right? I'm just replacing a with e to the log a. And then because the natural exponential function raised to an exponent has this property where the exponents multiply, then there we go. So a to the power x is the same as e to the power x natural log a. So there's the connection. There's the connection between general logarithms and the exponential, or the natural exponential function. We can do the same sort of analysis with a general logarithmic function. This dude, log base a of x, has to be the inverse of the function a to the x. So let's just go through the procedure for constructing inverses. A to the x is the same as e to the x log a, as we've just discussed. So we want to find an inverse to this function. We want to find an inverse to the function e to the x log a. So what is the procedure? Well, we set up the equation, and then we need to solve for x. So if the variable that we're interested in is stuck in the exponential position, then what we do is we take logs of both sides. So log y is equal to log all of this. And now, because the natural log and the e cancel each other, we just have log y equals x log a, right? This natural log and this e cancel. So divide both sides by log a, and we get x is equal to log y over log a. So then the final step in constructing the inverse is we interchange x and y, right? So if we interchange x and y, then this becomes log x over log a, and then over here we have the inverse function, which we have been calling log base a. So there we go. The log base a of x is the natural log of x over the natural log of the base. There's the connection between general logarithms and natural logarithms. Not too hard. I mean, it follows pretty much immediately from all the definitions and the properties that we have already established. So, as a matter of fact, we can define these expressions by way of these formulas, because the natural functions are already perfectly well defined. The fundamental theorem of calculus gives us their definition. So, it's actually easier to take these general expressions and just define them in terms of the natural expressions. That's another reason why we would call ln and e natural expressions, because they arise from another source, from a natural source, from the fundamental theorem of calculus. So log base a is defined as the natural log of x over the natural log of a, provided everything is well defined. So a has to be positive, because otherwise the natural log is not defined. Similarly, x has to be positive, and a can't be 1, because if a is equal to 1, well, the natural log of 1 is 0. So this would be telling us to divide by 0, which of course we can't do. Similarly, a to the power x is defined, so when I write colon equals, that means, by definition, that means this expression is defined to be equal to this expression. And here, the only restriction is that a has to be positive, again, because we're taking its natural log, but there's no restriction on x at all, because the exponential function can take in any real number, right? Its domain is all the real numbers. So I'm not going to go through it, but it is easy to prove that all of the laws of logarithms and laws of exponents that were derived for the natural functions also hold for the general functions, as we would hope. They follow almost immediately from these definitions, so I'm not going to go through it. It's pretty easy. It's pretty easy to prove. So this is all the same as everything that I've written before, just with a instead of e. The one sort of new law of exponents that comes up is this one, that if you have ab to the power x, that's the same as a to the x, b to the x. So we have that. So I make a note of limits. Limits as x approaches the edges of the domain. And we have to be a little bit careful when we're talking about the limits of general exponentials and logarithms, because the asymptotic behavior, which is to say the behavior as you approach the edge of the domain, depends on the base. It depends on the base here. So rather than go through all of these formulas here, let me actually show you the graph, because looking at a graph of these things, it makes a lot more sense. And hopefully this is review. Okay, so if the base is larger than 1, so say for instance you have 2 to the power x, then we have an exponential growth curve. It looks like this. So it rushes off to positive infinity as x goes to infinity, and it goes to 0 as x goes to negative infinity. The logarithm base 2 is going to be the inverse of this. So, to get the graph of an inverse, you just reflect about the 45-degree line. So reflect f about the line g. And there you go. So there's the graph of the logarithm base 2. And it looks qualitatively similar to the natural logarithm, right? What does the natural log look like? The natural log looks like that. So it's pretty much the same shape. It's just the very slight details are different. But it has the same asymptotic behavior, at least. So this is the case if the base is larger than 1. If the base is smaller than 1, then what do we get? So let's say the base is, say, 1/2. So 1/2 to the power x. So notice, now, it has the same shape as 2 to the power x. It's just been reflected about the y-axis. So instead of being an exponential growth curve, it is now an exponential decay curve. So as x goes to negative infinity, it goes to infinity. And as x goes to positive infinity, it goes to 0. Incidentally, because 1/2 is the same as 2 to the power negative 1, this is exactly the same as 2 to the negative x. Right? Those functions are exactly the same. So if you see an exponent with, or an exponential function with a negative in the exponential position, that indicates more often than not that you're looking at a decay function. Exponential decay rather than exponential growth. If we were to look at the log of this, well, again, that's just the reflection about the 45-degree line. So this is what the natural, or this is what the logarithm base 1/2 looks like. So as x goes to infinity, it goes to negative infinity. As x goes to 0, it goes to positive infinity. So, yep. So that's basically all I'm saying in all of these limit formulas. These limit formulas all follow from just examining the graph. So, I wanted to mention, and I have been mentioning continually throughout these last few sections, that we have been calling these functions logarithms, and we have been calling these functions exponentials, but we have never made any reference to the traditional definition of exponentiation as being repeated multiplication. I mean, yeah, as I've already said in this lecture, we have come at this from a completely different direction. So, I want to just finally establish that the notion of exponentiation that we have been discussing, namely as the inverse of this definite integral, is actually identical to the traditional notion of exponentiation. Now already, the fact that it follows all of the same laws should be proof enough. And indeed it is, because all of the properties of exponentials that we are already familiar with from algebra follow from these laws. So, for example, let's go back to 4th grade. When n is a positive integer, a to the power n should be a multiplied by itself n times, right? So, with our new definition, does this really hold? Well, yeah, it does, because n we can write as 1 plus 1 plus 1 plus 1 plus 1, n times. And then because of this property here, property 1, this is the same as a to the power 1 times a to the power 1 times a to the power 1 times a to the power 1 n times. So, indeed, we have recovered the traditional notion of exponent, even though we came at it from this completely unexpected direction. What else do we know about exponents? Well, we know that anything raised to the power 0 has to be 1. Is that true of our new exponents? Well, yeah, it is, because by definition, this is the same as e to the power 0 log a. Well, 0 times anything is certainly 0, and e to the power 0 was 1, by definition. Right? Go back to the notes for the previous section, and we know that if we plug 0 into the exponential function, then we get 1. What about a to the power negative n, where n is a positive number? So it's like a to the negative 2, something like that. Well, Again, from algebra, we know that this thing should end up being a reciprocal. And indeed, this is the same as a to the power 0 minus n. Now, by this rule here, subtractions turn into divisions, and a to the power 0 is 1, as we've just established. So indeed, a to the negative n is the reciprocal of a to the n. The only other rule from algebra that we have to check is the rule for fractional exponents. So remember, if you have a to the power m over n, that is the same as the nth root of a to the power m, right? The denominator gives the root, and the numerator is just a power. Do we have this? Well, indeed we do. So a to the m over n, if we raise this to the power n, then by this property, exponent raised to an exponent, we get multiplication. So m over n times n is just m. So a to the m over n is an nth root of a to the power m. Well, which nth root? Because we know we have, if n is even, then we have positive and negative roots. Well, a to the m over n, by definition, is e to the m over n log a. And the output of the exponential function is always positive. Again, check the lecture notes from the previous section to see that the exponential function, by definition, always has to give us positive numbers. So it follows that this is the positive nth root of a to the power m. So indeed, it is a consequence of these formulas, really just 1, 2, and 3, that this new definition of exponentials that comes from calculus agrees perfectly with the traditional notion of exponentials that we got in elementary school. And that's fascinating to me. That's really magical that we have recovered, that we have been able to recover traditional exponentials from such a weird direction. Which is basically all that I say here. And more than that, really, when you're in elementary school or high school, you only go up to fractional exponents. But what if the exponent can't be written as a fraction? What if the exponent is pi, right? What if the exponent is irrational, so you can't write it as a fraction? What do you do then? Well, now we actually have an answer, because since a to the x is e to the x log a, x can be any number we want. It doesn't matter if it's an integer or rational or irrational or what. We're basically just throwing it into a natural exponential function. And the natural exponential function doesn't care what it's being fed. It's perfectly well defined for any real number, even if the real number is irrational. So yeah, that's why we define this expression in terms of the natural logarithm, because in so doing, we allow this expression to be defined for every single real number, not just the ones that can be written as fractions. So not only have we recovered the earlier definition of exponent, we have actually expanded it. We have expanded it to be able to take care of irrational numbers. So that's incredible. Now, another benefit to writing general exponentials in terms of natural exponentials is because we have already determined all of the calculus rules for differentiating the natural exponential and natural log functions. So that means we can figure out the calculus rules for general exponentials and logs pretty easily. So in particular, a to the power x is e to the x log a. So if we want to differentiate this, well, what's the rule for differentiating exponentials? You just leave it alone, right? Leave it alone. And then multiply it by the derivative of the exponent. So what's the derivative of x log a? Well, log a, because log a is just a constant, right? So literally all we've done is we've just plopped out a factor of log a, and then all of this junk is just a to the power x again. So the derivative of a to the x is just a to the x log a. So it's the same We just have to multiply by this additional factor of log a. Similarly, for a general logarithm, the log base a of x, well, by definition, this is the same as the natural log of x divided by the natural log of a. Well, 1 over the natural log of a is just a number. It's just a constant, so the derivative ignores it. So really all we're doing is we're just differentiating natural log x, which is 1 over x. And then this 1 over log a is a constant, so it just hangs out. So I record these observations in the box below. So here I'm just generalizing it a little bit by using the chain rule. So if we have a to an x to a whole expression, then this is log a, derivative of the expression a to the f. So leave it alone, multiply by the derivative of whatever is up here, and multiply by the log of the base. That is the rule. Similarly, if we have the log base a of an expression, well, that is, so it's 1 over log a times the expression times the derivative of the expression. This is just the chain rule. Yep, so these are the formulas. Notice that these are exactly the same as the formulas for differentiating the natural exponential and natural logarithmic functions. The only difference is we have these additional factors of natural log of the base popping out. So in the case of differentiating the exponential, we multiply by log a. In the case of differentiating the logarithm, we divide by log a. But aside from that, it's the same rule as with their natural counterparts. Okay, so differentiate 10 to the power x squared. So here we have something of the form above, 10 to the power x squared. So this is literally just an application of the formula. So in this case, a equals 10. And f of x, the thing it is being raised to, is x squared. So this is just natural log 10. So this is just natural log 10 times the derivative of x squared, which is 2x, times 10 to the x squared. And that's it. That's all there is to it. For some reason, this is making me uneasy. Having this... Let me do this. There. I don't know. That looks a little bit better to me. One moment. So next, differentiate the log base 10 of 2 plus sine x. So again, this is just a literal application of this formula that I've written. So a is equal to 10, and f of x is equal to 2 plus sine x, in this case. So the derivative of this dude is equal to, so it's the derivative of whatever was inside the log. So the derivative of 2 plus sine x is 0 plus cosine x over log 10 times f of x. So that's it. That's all there is to it. So super easy. Super easy. Just an application of the formulas. So by the same token, finding the antiderivative of general exponential functions is easy. So the antiderivative of a to the x, well, by definition, a to the x is e to the x log a. And remember, we had a formula from the previous section. The antiderivative of e to the x times a constant, and log a is just a constant, well, that is e to the x log a divided by the constant. So this is literally just 1 over log a, e to the x log a. And then e to the x log a is a to the x. So we arrive at this formula. So the antiderivative of a to the x is just a to the x divided by natural log a. So here's an example, which is literally just applying this formula. So the antiderivative of 2 to the x is 2 to the x divided by log 2. That's it. That's all there is to it. Now, because this is a definite integral, we have to deal with the upper and lower limits, but, I mean, that's easy enough. Let's see. So 1 over log 2 is a constant, so let's factor that out. And then we have 2 to the power 5 minus 2 to the power 0. Okay. 2 to the power 5 is 32. 2 to the power 0 is 1. So 32 minus 1 is 31. So our final answer is 31 over log 2. And that's all there is to it. So, I want to draw your attention to the distinction between power functions and exponential functions. Power functions are things of the form x to the power n. Namely, the base is a variable, and the exponent is a constant. So things like x squared, x cubed, x to the fourth. Polynomials. Any polynomial is just a combination of power functions. With power functions, we use the power rule, where this becomes n x to the n minus 1. Now, the sort of functions that we have been looking at here are not power functions, because for a power function, the base is a variable, and the exponent is a constant. Well, we've been looking at the case where it's exactly the opposite. The base is a constant, and the exponent is the variable. So I just want to draw your attention to that. I don't want to see this. Right? I don't want to see the derivative of 2 to the x is x 2 to the x minus 1. I know someone is going to do it. I know for a fact that someone is going to do it, but this is completely incorrect. That is incorrect because this is not a power function. If it was x squared, then that would be right, but it's not. The role of the variable and the role of the constant have been reversed. So, so the correct derivative would be, well, what's the rule? It's just log a times the derivative of whatever was on top times the thing. So it's log 2 times the derivative of x, which is 1, times 2 to the x. Right. So it's unchanged. You just multiply by the log of the base. Now, what about something like this? X to the power root x. So this example really fits into neither of the two cases before, because with a power rule, the base is a variable and the exponent is constant. With exponential functions, the base is constant and the exponent is variable, but with something like this, we have a variable both in the base and the exponent. So the thing is, for something like this, neither the power rule nor the rule for exponential functions are valid. And in fact, I say this here. Neither rule is appropriate. So the strategy that we employ here is a logarithmic differentiation. So since there is a variable in both the base and the exponent, we need to use logarithmic differentiation. So what are the steps in logarithmic differentiation? Well, first, take the log of both sides. The natural log, that is. Well, I guess it doesn't really matter. It can be any log, but natural log is going to be the easiest. Has the least amount of associated baggage. Now differentiate both sides. So the derivative of log y is y prime over y. Oh, I'm sorry. Wait, before we do that. The reason we took the log in the first place is because we can take advantage of the laws of logarithms to simplify this dude. So the square root x in the exponent can be pulled out front. Yeah, of course. That's the reason why we take logs in the first place. Okay, now differentiate both sides. So the derivative of log y is y prime over y. The derivative of the dude on the right, well, we're going to have to use the product rule. So differentiate the root, leave log x alone. Leave root x alone. Differentiate the log. That is how we will do it. So the derivative of root x is 1 over 2 root x. Right? That's just the power rule. Because we have x to the power 1/2. So bring that down. We get 1/2 x to the minus 1/2. Times log x. Plus derivative of log x is 1 over x. So we just get that. Now we are interested in y prime, right? Because that's what we want in the first place. We want the derivative of y. So now let's just solve for y prime by multiplying both sides by y. So there's that. You know what? I don't like this root x over x. Because square root x is the same as x to the 1/2, and this is the same as x to the 1. So power of 1/2 on top, power of 1 on the bottom, the exponents subtract. So this is 1/2 minus 1, so this is minus 1/2. There. So finally, we want our final answer to be in terms of just x, so let's replace y with its actual identity, which y was x to the root x. Okay. And this is, I really want to simplify this because these denominators are so close to being the same. So common denominator is 2 root x, log x plus 2, like so. And let me write this as 2 plus log x, there. That looks a little bit nicer because now the 2's are sort of aligned, and also there's no way that you can confuse that for log of x plus 2, right? It's not log of x plus 2, it's log of x plus 2. Anyway, I'm just being pedantic. So, there we go. That's pretty much all that I have to say for this section. I mean, the main takeaways, of course, are these formulas. So this allows you to differentiate any exponential expression with a generic base. This allows you to differentiate any logarithmic function with a generic base. Here's the antiderivative for exponential functions. It's easy. It is, don't change anything, just divide by log a. Probably the strangest bit, or maybe the most challenging bit from this section, would be differentiating things like this. So if there is a variable both in the base and in the exponent, then you need to use logarithmic differentiation. That's the only... I don't know if that's the only strategy that'll work, but that is a strategy which will work. Okay, so that's it for this one.